will the source code be posted anywhere? I'm not, uh, I'll get back to you on that. Yeah. Okay. So problem 3. So you're given some string of DNA, and then um, basically for you have like these pairs of uh like the form K and L, and it's like um okay. Yeah, so for each string of length K, um yeah, so basically you have your string of length N, and for each string of length K, uh you pick um basically pick the first occurrence of the lexicographically smallest sequence of length L. So this is K and this is L. And then yeah, yeah, and then like yeah, so basically yeah, this is your whole string, this is your whole string. And then for each pair KL, um you consider like a substring of length K, and then you pick the lexicographically smallest substring of that which has length L and the leftmost occurrence of that. So that's at some index I, and then you add this to a set. Um, and then yeah, so for yeah, so basically size of P. So P is basically a set and is constructed by taking all windows of length K and then the lexicographically smallest substring of that of length L and taking the leftmost position. So if there's an index I such that is true, then you add I to your set P. So basically, yeah, so you can consider this like you're iterating over all the windows of length K, and then you're taking the lexicographically smallest thing of length L. So there's the first iteration, and then there's the second iteration, uh, and then you're taking the lexicographically smallest thing of length L, and then you're adding this index to your set, and then you're adding this index to your set. Yeah, and then the third time, I guess you'll shift the K to the right, and then the lexicographically smallest thing of length L will add this index to your set. And what this question is asking is, so basically given K and L, you have a set P and that P has a size. So for each V in the range from 1 to N, how many K L pairs are such that size of P is equal to V? Yeah, so this is a mouthful, but yeah. So for each K L pair, you can construct a set P by looking at the distinct indices of where the smaller string starts, and then add that to your set P. And then for each size, how many KL pairs have that size, right? Yeah, so that's the problem. And then uh, you have N is at most 3,000. So yeah, uh, and there are some subtasks which have like um, that are a bit lighter. So it's like N at most 500 and up to 100. So like, I guess this subtask is probably like N to the fourth, and then this is N cubed. And then this is, uh, yeah, this is N squared. Yeah, so I'm going to talk about how to do this in N squared, and I guess maybe slower implementation of this might result in a complexity of N cubed or N fourths. Yeah. So let's fix the length L, right? Fix the length L, right? Um, and then, yeah, and then suppose we fix the length L. So, yeah, so I guess like this solution will be, um, I'll be, it'll end up being iterating over L and then solving something that takes O of N time, right? So fix L. And then right now we're just gonna assume we know how to do some certain things like comparing two strings of length, substrings of length K, but I'll go more into detail after we explain this idea. So goal is to count, so for each V, 1 to N, count number of KL with this fixed L with size of P is equal to V, right? Yeah. So what we can do basically, if you fix L, so let's consider the contribution of this. Let's say you have a substring of length L. Let's try to see which values. So you have a substring of length L, which starts with I. So let's try to see which K values this I is counted in, right? So in order for this to be counted in a KL pair, what you basically need is, so K is going to be some outer window, right? There's going to be some outer window where L is a substring. So yeah, so the size of L is a substring of this, and the size of L, this thing of size K, this is a substring of this, right? So we want to see for how many K, I is in the answer, right? So let's just say, assume we have a window of length K, and this is equal to L, like this index here is equal to L. And then let's say this is the last string of length L, right? Let's say this length is L, right? So this is going to be lowercase r, right? So we should try to see like in what case, if we have this window of length K, or for what windows will I be counted, right? So basically what we have is that just consider all the substrings of length L that are possible. So basically what we have is that this needs to be the first substring of length L that is the smallest value, right? So basically all the substrings that start from here are going to be greater than Ti. So yeah, so we can just define some notation. So we can define Ti to be the substring of length L that starts with I. So it's like Si up to I plus L minus 1. So we need that all these substrings that start here have to be strictly greater than Ti, because this is the first substring that's equal to the lexicographically smallest. And then all of these substrings from I plus 1 to R have to be less than or equal to Ti, right? And then let's just assume something, which I'll explain how to do later. Assume we know how to compute like strings of length L and O of 1 time. Yeah, if you don't have this assumption, then I guess you can still pass like the simpler subtasks. Assume we know how to compare two substrings of lengths L in O of 1 time, right? So basically, you can think of each substring as like an element, right? And then basically the restrictions for your window, you can have any window LR, restrictions for the window. So the window of length K is that, yeah, so all of these need to be greater than or equal to Ti, and then all of these need to be less than or equal to Ti. So basically, like if you consider a maximal window, then the L will be like uh first element greater than equal yeah uh, wait sorry is okay yeah, so it's basically you're looking at the nearest element that's less than or equal to ti plus 1. So nearest element less than or equal to ti plus 1, right? Because this thing it's just for a maximum size window, right? Since this one is going to be less than or equal to ti, so it's basically 1 to the right of the nearest element less than or equal to ti plus 1. And then restriction for r is going to be um oh, sorry, this has to be greater than equal to, yeah, that'll make more sense. Yeah, basically since this has to be the smallest one. Yeah. And then the restriction for r is going to be the nearest element to the right that's strictly less than ti. Strictly less than ti plus 1. And we're just assuming that we know how to compare two substrings of length L and O of one time, right? So this is something you can compute for every I and O of n. Yeah, so it's like a problem we can do with stacks. Yeah, it's called nearest. Yeah, so it's one application of stacks. It's called nearest smaller element. I'll paste that in the chat here. So it's something you can do with stacks. Basically the idea is like if you have an array and for every I, let's just consider this problem, nearest element less than or equal to ti. Um, basically, you go from left to right, and then you maintain a monotonically going up stack. And then if your new element is less than the previous element, then you can pop stuff up out of the stack and then insert the new element. So the nearest element less than or equal to ti was going to be this. Yeah, but you can feel free to refer to the link I sent, USACO guide stacks. This explains how to do these kinds of problems. Like if you're given an array, how do you find the nearest smaller value or nearest larger value? Yeah, so like more directly, it's an application of this CSES problem, nearest smaller values. Yeah, so basically you can apply the trick that or the technique used in nearest smaller values to be able to compute L and R right, like this, right? For every I in O of n time, right? So suppose we have L and R, right? Then the minimum, the minimum, this gives a range of K for which I contributes. So basically, um, this substring of length L contributes. So K has to be at least L, right? So L is less than or equal to K. And um, then we have our left bound and our right bound, right? And then this has additional, how would you rank the problem difficulty? What do you think about overall difficulty of silver test? Yeah, so I might talk about this a bit later, but yeah, I would say this is probably I would say this is probably harder than usual silver. Yeah, like this problem could have also been good for gold. Especially problem 3 is probably advanced. Yeah, but we can talk about this near the end. Yeah, but yeah, I think it's still useful to solve this thing. Pretty instructive. Yeah, but yeah, I think US Open is probably on the harder end. Yeah. Um, yeah, so the possible K values. So the minimum K is basically the one that encloses L, and then the largest K is basically is gonna be like the right side is like R plus L minus 1. So it's gonna be something like uh R minus L plus L minus 1. Yeah. So basically K I contributes to every K in this interval, right? So we can try to maintain. So for every I, we basically have a range for which I contributes to, right? It contributes to this interval from L up to L minus R plus X plus L plus 1, right? So basically, we can try to have an array, and ideally we want AI to be like the size of P. Yeah, so for like any value K, we can let A of K to be like the size of P for the pair KL, right? So we want to be able to compute this, right? Right? So we're fixing L and we're just considering different Ks. And then we want to find the size of P for all KL, right? So the point of fixing I is that we see which Ks that it contributes to. So basically, uh, what the spiel here, when I'm concluding that K is going to be in this range from L to R minus L plus L minus 1 in order for I to have a contribution, you can think of this as an operation given a left boundary and right boundary for K. Add plus 1 to xy, where xy is a range. Right? So basically for each I, I'm going to have this kind of operation, add plus 1 to a range xy. And then at the end, I want to output the value. Yeah. I can write this a bit more clearly. So basically for everything in this range from x to y, so add plus 1 to a from range x to y. This is my operation, and I have like O of n of these operations. So naively, if I try doing this, it will be O of n squared time, but there's a way to speed this up. So yeah, so like I want this array A, which is the size of P for all the pairs KL for fixed L. But directly doing this is too slow, but we can do something called difference arrays. So basically we can let BI, we can create a new array B where BI is equal to AI minus AI minus 1. Then we have, yeah, and then we can also like for edge case, we can have like B1 is equal to A1. Then if we can construct this difference array, then we can reconstruct A because AI is going to equal the prefix sum over I of BI. So let's try to think about how we can compute this array BI. So the original goal is to add plus 1 to A from the range x to y. And that's equivalent in this difference array. So if you want to add 1 to range x to y, basically ax plus 1 minus ax doesn't change. Ax plus 2 minus ax minus 1 doesn't change. The only things that change are ax minus 1 and ay plus 1 minus ay. So basically this operation is equivalent to add plus 1 to bx and then add minus 1 to by plus 1, right? So this operation, add plus 1 to ax up to y, the same thing as add plus 1 to bx, and then add minus 1 to bx minus y. And then this gives us the answer, right? So we know for fixed L, the size of P for all the K. And then we can do this for all L, and then we have our answer, right? So we know for each K and each L, what's the size of P. So everything we did here was O of n, right? So fix L, and then you do this kind of stack thing, which is the CSES problem, where you find the nearest element less than or equal to in the left, and then the nearest element less than to the right for all I. And that gives you for a range of K for which I contributes to. And then you're doing these operations where you're adding plus 1 to a range. And then you can make a difference array out of it. And then the answer is the sum of the difference, prefix sum of the difference array, right? So this gives you the size of P for the pair KL. And our assumption was we know how to compare two strings of length L and O one time. So I'll go over how to do this. So this is this is an idea that comes up in more advanced problems, but we can let dpij be like the longest common prefix of the suffix starting from I. So LCP is the longest common prefix of the suffix starting from I and then suffix starting from J. So we want to be able to compute this dp value. And the idea is you sort the suffix, sort all the suffixes of L. So so you have the suffixes in sorted order. And then if you want to find, so if this is like A, B, C, A, C, D, A, B, C, D. Basically, the longest common prefix of this is 2, and then the longest common prefix of this is 1, right? Because A is the longest common prefix for these two, and then AA is the longest common prefix for these two. And then if you want to find the longest common prefix of this, it's going to be min of the longest common prefix of this and longest common prefix of this. So it's going to be 1 because it's the min of 1 and 2. So you have O of n suffixes, and then it takes n squared time to find the longest common prefix for the adjacent ones, right? And then we can do an O of n squared loop where you compute longest common prefix between all the pairs. So this allows you to get dpij. So so the time complexity of this is going to be n squared. So let's assume that we already computed dpij. Yeah, so there's some details to be able to compute the longest common prefix, but let's assume you already computed this and you have access to this for free. Now, how do you tell if two substrings of length L, if it's less than, or if it's greater than, or if it's equal to, right? So let's consider like Si up to I plus L minus 1, and then Sj up to J plus L minus 1. So there's 3 cases. So case 1, longest common prefix is greater than or equal to L. So basically that gives us that this string is equal to this string. So both are equal. And then case 2, LCP is less than L. So basically this is the LCP, and these are the 2 substrings of length L, right? So these 2 things are equal. And then to check if this is smaller than this, you have to check if this is less than this or greater than this. So compare, so let's just call this A and call this B. Then just compare A, LCP. So you're just comparing 2 characters, LCP with B, LCP. And since this is the longest common prefix, these 2 things are guaranteed to be different, right? And if A of this is A and this is B, if this character is less than this, then A is less than B. If this character is greater than this, then A is greater than B. Yeah, so that's the idea of how to be able to compare 2 substrings in O of 1. Because we could pre-compute the LCPs, we pre-compute the longest common prefixes, and then this allows us to tell in O of 1 if one string is smaller than the other. Yeah, and since we have a way to tell in O of 1 if one string is smaller than the other, then this whole thing works in O of n. Yeah. So that's problem 3. I guess I'll briefly just restate what we did. So we just fixed L, and then we count, we solved the problem for each V in 1 to n, count the number of KL pairs with the size of P is equal to V, and then for any I that could potentially be in P, we check for which K values could I be in P, and that corresponds to adding +1 to a range. And it's naively, this is kind of too slow, so we take the difference array bi is equal to ai minus 1. And then you, uh, yeah, you can do this in a constant amount of time, and then um, you can reconstruct the answer, and yeah, but just by taking prefix sums, and then you do this for all L to be able to do this in n squared. Yeah. So that's the solution for um problem 3. Yeah. Uh, yeah, just checking, is the plan still for Andrew Shu to present problem 2? Just want to check. Otherwise,
I don't think so. I think he said he'd be
okay,
out for, yeah.
so I can present it. Yeah.
Yeah,